some stuff with the double pendulum. And contrary to popular belief, I'm not going through puberty, I just have cold, so hopefully you can understand me just fine. This is lecture 7, double pendulum. So this is basically the double pendulum we're going to do our experiments on. So this is a bit different from the ideal double pendulum, of course. So we'll look at both cases and we'll see what happens. So let's draw basically that, except in an idealized case. So let's say we have some pivot there and some rod that does not have a mass. And then some point source there that's connected to that has some sort of pivot there. And then another massless rod, and then another point source. So we're going to be thinking of something like that. Where the two have different masses and different lengths as well. It's all one. So we're going to have something like that. And let me just denote this angle. So say that's theta 1. And then that angle, say that's theta 2.
Wait, is theta 2 with respect to theta 1 or the
So this is with respect to the vertical.
Okay.
Yeah. So that's basically what theta 2 is. So we're going to have that sort of setup. And this is all in the PDF notes, by the way. So all the details will be in the PDF notes. Okay, so we want to figure out, or how do we want to deal with this? We know a few ways that we can get the equations of motion, but what do we use for a very complicated system like this? What did we use for complicated systems prior to this? Okay, what do we use for simple systems? So let's say we have a simple mass on a spring system. What do we use for the equations of motion? Whose law? Okay, so we use Newton's laws for simple systems. But here is a more complicated system, so using just Newton's laws would be very difficult. So we have to use another famous person's idea. So who's that?
Lagrange?
Yeah, so we're going to put this in the Lagrangian framework and then find the Lagrangian, use Euler-Lagrange equations, and then get the equations of motion that way. So for the Lagrangian, what do we have to do? So as we recall, the Lagrangian is the kinetic energy minus the potential energy, right? So what's easier to find here, though, the kinetic or potential?
Potential.
Okay, so the potential energy is going to be a lot easier to find than the kinetic. So let's go ahead and try to find the potential energies. So let's find the potential energy of the first one, so first pendulum, or first arm, let's say. So how do we want to define the potential energies, though? Like, it doesn't really matter what the absolute value of the potential energy is. What matters is how the potential energy is changing, right? So we can define the potential energy any way we want, but what's a convenient way to define the potential energy? How do you want to define it when the pendulum, so if we're thinking of this pendulum, how do you want to define it if the pendulum is at rest on the bottom for the top part? What do you want to say the potential energy of that is?
Zero.
Zero, right? So on the bottom, so lowest point, lowest point, it's going to be like this. So this is, let's see how I write it. Okay, theta 1 is 0 there, right? So at the lowest point, u is going to be 0. Right? And we can also have the top pendulum going all the way over here, right? So what is it at the highest point?
0.
It's not going to be 0 at the highest point.
Max.
It's the max. So what is, so let me just write it. So theta 1 equals plus and minus pi. So what is u for that case? So if we're saying the lowest point is 0, right? So we're starting at 0, then what is it going to be if we're above that lowest point, or twice above that lowest point?
Like 2m1gl1.
Mm-hmm. So it's going to be 2m1gl1, right? So at the lowest point, it's L away from this line. At the highest point, it's also L away from that line, but in the other direction. So at the highest point, it's going to be 2L away, right? So it's just like, you know, if you lift anything up. If you're at the lowest point here, then it's 0, and then say this is L, and then this is 2L. So at the highest point, it's going to be 2m1gl1. So this is the way we want to look at our potential energy. But what is it going to be in between, do you think? So what would we have to do for that? So what do we have here? What useful mathematical tool can we use? So what do we usually use in these sort of situations? So we have some angle, we have some lengths.
Polar coordinates.
Well, we don't have to use polar coordinates, but we can use this triangle, right? So we can figure out what this is, right? Because the potential energy of this is just dependent on the height, right? So all we have to do is figure out what the height is. So what is this height going to be?
Maybe sine theta.
Sine or
L1 cosine theta.
cosine, right? So this height is going to be L1 cosine theta 1. But notice that at the lowest point, it's at 0, right? So how high is it from the lowest point if this is L1 cosine theta 1?
Minus L.
So
Do we say how high it is from the lowest point?
do you want to say minus L or the other way around?
Oh, L minus L.
So L minus this, right? So here, the potential energy is going to depend on the entire length minus whatever amount it's being pulled up, right? So in between, we get that U is going to equal 2m1 g L1 times 1 minus cosine theta 1, right? So at the bottom, it's 0, and then the amount that it moves up is going to be L1 minus L1 cosine theta 1. So that's what we get for the potential energy of the first one. So the second one is a bit trickier, though.
Wait, if when you're at pi or negative pi, wouldn't that account for the factor of 2? Or am I missing?
Oh, you mean plugging it in here?
Right.
Yep, yeah, exactly.
So did you need the 2 out front then?
Oh, I don't know why I put
it
a 2. Yeah, sorry. Yeah, that was
Just wanted to make sure.
silly. There we go. That's right now. Yeah, yeah, it's a good catch. Yeah, so it's just M1 G L1 times 1 minus cosine theta 1. Yeah. So anything else about this? I think it's right now, right? Yeah. So that second arm is going to be trickier though.
Yeah.
So, of course, at the lowest point, it's going to be 0. At its highest point, it's going to be 2m1 g times L1 plus L2, right? But in between, it's going to be a little different. So let's see what it is. So over here, we're going to have that this is L1 cosine, or sorry, L2 cosine theta 2, right? So we have that for the height here. We have this height, and we know what the lowest height is. So we're going to do the same sort of thing. So we're going to have, so at the lowest height it's 0. So what is it going to be then? So it's definitely going to be, U is going to equal M1G. So we're going to have that. And then what do we have?
L1 plus L2.
I see what you're saying. Okay, so L1 plus L2. Let me just think about it for a minute. Okay, so L1, L2, and then you want to see the difference? Yeah, okay.
But shouldn't they have two different thetas, or it should be like theta, it should be B, right? So.
Well, theta 1 and theta 2, right?
Oh, okay. Oh, yeah, theta 1, theta 2, yeah.
So yeah, it's going to be L1 plus L2 minus 1. So it's
minus,
just, yeah.
Minus L1 cosine 1,
Okay.
theta 1. Minus L2 cosine theta 2.
So that's it, right? So then we're going to have M1G times L1, 1 minus cosine theta 1, plus L2, 1 minus cosine theta 2. So we're going to have that, right? So this is U2 and this is U1. And then just for the total potential, it's just going to be U2 plus U1, right? So we're going to have this for our potential energies. So any questions about getting the potential energy? So the potential energy is the easy part. That is just determined on the height. The kinetic energy is going to be difficult though. So what do we need to do for the kinetic energy? So there's no rolling here, right? So we're only looking for the translational kinetic energy. So which direction is this thing going to go?
Angle.
Okay, but like at this particular point.
Travel like, well, to the left. Is that what you're trying to say?
Or either left or right, right? It depends on the initial velocity that it has, but which direction, so in comparison to the circle, which direction is going to go? It's going to be what to the circle?
Perpendicular?
Not perpendicular. The other way.
Orthogonal?
No.
Parallel? No.
So how do objects move if it's moving in a circle? What?
Clockwise or counterclockwise?
Well, okay, but what direction does it have the tendency to go in? Let's say you're spinning something and then you just remove that rope. Tangentially, right? So it's going to be tangential to this. So let's write it in black, let's say. So this is going to be tangential. So we're going to have, I'm going to try to draw a right angle. So it's going to be something like this, right? And then that vector is going to be what? So that's going to be the velocity vector. But how do we find the velocity compared to the angular vector? To the angular velocity.
Could you use, well, like it's, normally you say theta times the radius is the
Yep, that's it.
arc
Yep.
length, and then just take the derivative for velocity?
Exactly,
Is
yep.
that it?
So what is it going to be here?
So it's,
So what's the radius here?
it'll be L1
Uh-huh.
times theta 1 prime,
Yep. So theta 1 dot.
or dot.
So we're going to get that for the tangential velocity, right? So for that we have, so that's the first one. So for the first arm, T1 is going to equal 1. So we have the tangential velocity and we have the mass.
1/2 m1 times L1 theta 1 dot.
Squared, right?
Yeah.
So we get that. So that's the kinetic energy of the first arm. Now we have to find the second arm. So that second arm is what's going to be difficult. So what happens with the second arm? So let's say it was stiff. I don't think I have, I don't have the little washer, I don't think. Let me see. Yeah, I don't think we have the washer here. I don't know what I did with it. But anyway, let's pretend that the second arm is stiff on this, right? So let's say that the movement is just due to that first arm, right? So then what's the velocity of that point on the bottom?
L1 plus L2 times theta dot.
Well, it won't be quite that, right? So it's just stiff, right? So is the velocity of the second arm changing at all? Or is the velocity of that second arm changing compared to the first arm, I should say,
Oh, no.
if it's stiff, right? So if it's stiff, I mean, if you have it stiff this way, then you can see immediately, right? So that velocity depends on that first arm. If it's stiff this way, then that velocity will depend on that first arm, right? But now, if we let it move, then the velocity will depend on that first arm and the velocity of itself. So the velocity will depend on the velocity of the first arm and the velocity of the second arm compared to the first arm, right? So we can find what the velocity of that first arm is fairly easily, which is going to be just L2 theta 2 dot. But we also have this velocity on it as well. So it's going to be as such. So this is going to be L1 theta 1 dot. So now we have to deal with these two velocities. So what do we do?
Add vectors.
Yep, so we just add the vectors, right? So that gets tedious. So that's going to become, so T2 is going to be 1/2 M1 times L1 squared theta 1 dot squared plus L1 L2 L1 L2 cosine. I'm going to check this real quick as well. Cosine of theta 1 minus theta 2 plus L2 squared theta 2 dot squared. So let me see if that's correct. Oh, I need a theta dot out here. Yeah, that's what I forgot. So I need this to be plus L1 L2 theta 1 dot theta 2 dot. So that's what it's going to be when we add the vectors together.
Do we take like the magnitude of it? Is that like the magnitude of it, or?
Nope, that's just adding the vectors together. Yeah, so that's just taking this vector and adding it to that vector.
What about the second mass?
Yeah, sorry. This is going to be M2, right? So the only thing that's different is the velocity, but the mass obviously will be the mass of this. So that's a kinetic energy contribution from that second arm. So the entire kinetic energy will just be the adding these two. So it's basically a matter of finding the tangential velocities, except here it's tricky because you're going to have two of them acting on that second point mass. So after that we can use the Euler-Lagrange equations, but let me just write those down for you and then we won't actually do that. So Euler-Lagrange. That's going to be ddt of partial L partial theta 1 dot is going to equal partial L partial theta 1 and ddt of partial L partial theta 2 dot is going to equal partial L partial theta 2. So we would use Euler-Lagrange equations, but the algebra gets really complicated. So we're not going to do that here, but if you look in the PDF notes, you'll have all the details. So what I want you guys to do for homework is, so once you use Euler-Lagrange equations and you solve for, so you use these and solve for theta 1 double dot and theta 2 double dot. So I've done this for you. So basically what you would do is take these Euler-Lagrange equations, solve for theta 1 double dot, theta 2 double dot, but I have that for you on the PDF notes. So what I want you to do for homework is take the code that I send you for the matrix, for the matrix of the ODE, which is going to give you, we're just going to call theta 1 dot phi 1 and theta 2 dot phi 2. And what it's going to give you is four first order ODEs, and then you're going to use that, just use ODE 4.5 with some of the initial conditions that we're going to test out for our experiment, and then plot the trajectories using ODE 4.5. So I have the matrix and everything for you. All you have to do is just put in the initial conditions and plot the trajectories. So that's if we have the simplified form of a point mass. But now, let's say we wanted to do something like this, right? That's going to be a little different. So that's going to be significantly harder. So let's say that we wanted something like this. So we have it set up like ours, and let's say we have something like this. So maybe I don't want it so big. So let's say we have that, which is basically what ours is like. So we want to model this, and we want to use the same sort of procedure. So we're going to find the potential energy first. So what are we going to need for that potential energy, though? Where are we going to be calculating this potential energy from?
Center of mass.
So the center of mass, right? So we're going to have to figure out where the center of masses are. So it's going to be there, but we have to figure out how it's moving. So at some angle theta, where is that center of mass going? So this is... These are going to be the triangles that we're thinking of. So this is theta 1, and this is going to be theta 2. So that's theta 2. So we have something like that. And then we have, so this is, suppose that this is all of a uniform mass. So the density is constant there. The density isn't changing as we move. So this is going to be M1, this is M2. So we have to figure out how that center of mass is changing, right? So we know that potential energy is just going to be M1 G Y1 plus M2 G Y2, right? But now we have to figure out how y1 and y2 is changing as theta 1 and theta 2 are changing. So let's find out how y1 is changing. So that's just going to be for this. Oh, and I should tell you the lengths as well. So this is just going to be L1 and this is L2. So let's say they were straight, right? Let's say they're straight, and this is approximately where the center of mass would be. So where is that point if they're straight?
In the middle.
Okay, so it's,
Then have L1.
okay, so it's 1/2 L1, right?
Mhm.
So over here, this thing is 1/2 L1. So this is L1 over 2, right here, right? So then what's our y1? So this is our y1 over here. So what is y1 equal to?
Cosine 1/2 L1.
So L1 over 2 cosine theta 1, right? So that gives us our y1. Now how about our y2?
Is it sine?
Hmm?
Is it a sine?
No, so
Is it,
So- y2 I am going to define as coming down from the pivot all the way down here. All the way down to this point. So that's how I'm defining y2. So that's trickier. So this is y2.
Is it L1?
So that's going to give you this part. So this part will be L1 or L2 cosine, or L2 over 2 actually, cosine theta 2. But now we have to figure out that part. So how are we going to do that? So yeah, go ahead.
I would say, do we have to find the center of mass of both out of pendulum and like?
No, we don't have to do that. It's not. I mean, it won't be that complicated.
Oh, okay.
Yeah.
And then would you just add the distance of the one up there? The one.
Yeah. Hold on one second though. I did something stupid. So I believe this is how I want to define y1, but then this is not going to be the potential energy, right? So what is it going to be?
L1 with 2 cosine? It's going to be that?
So it's going to be, yeah, let's think about it. L1 over 2 minus y1. But no, y1 would do it, I think. Yeah, no, it would just be y1. Because, okay, so this is how I'm thinking of it. So you have the center of mass here, right? So that's going to give you your y1. So it's the distance the center of mass is away from the equilibrium position. So this is, but now do we have to subtract off that equilibrium position? I believe we would have to subtract off the equilibrium position. So we go from the equilibrium position to minus whatever this is. Let's see how I wrote it down though. So I just have it written as mgy1. Now is that going to be the same thing? Let's think about it. So we're going to have, but I have it written down as a negative. So I have m1gy1, and then I have y1 just as that, except I have this being negative here. I mean, we could define the potential energy as negative as well. That's fine too. So that's basically saying that at the equilibrium position, you have some negative potential energy. So that's basically how I defined it here. But we can define it slightly differently. So instead of doing it the way I did it, let's go ahead and do it the way we've been doing it and define our potential energy from the equilibrium position. So let me just keep this as positive, and I'm going to write this as L1 over 2 minus y1. So that when it's at the equilibrium position, so theta 1 equals 0, this is going to be 0. So let's define it like that here. So then we can continue with this. But first we have to find y2. So do we notice that this can be just continued all the way down, right? So this triangle and this big triangle has the same angle. So then what's this part of it?
Just be L1 cosine theta 1.
Mm-hmm. So that's just 2y1. So it's just L1 cosine theta 1. And then we add on that little piece,
L2
right?
over 2. Yeah.
So then we have L2 over 2 cosine theta 2. So over here, I want to define it from the equilibrium position. So that would be L1 plus L2. So L1 plus 2, L2 over 2 minus Y2. So that's how I'm going to choose to define it. So we're going to get this for our potential energy. But then for the kinetic energy, we have something slightly different. So what do we have to do for the kinetic energy? So we'll have the same sort of stuff we had, but we need what extra piece? So here we have something, a rod.
Rotational.
So we're going to need rotational, right? So we need a rod moving on some sort of pivot. So that's where we're going to get the rotational kinetic energy from. So we need to find 1/2 I omega squared, right? So I'll give you what that is. So that's going to be, so that is 1/24 times M1 L1 squared theta 1 dot squared plus M2 L2 squared theta 2 dot squared. So we're going to get that for the rotational kinetic energy. And then for translational kinetic energy, we just have this. So 1/2 mv squared is going to equal just 1/2 times m1 times x1 dot squared plus y1 dot squared plus m2 x2 dot squared plus y2 dot squared. So then for the total kinetic energy, we're going to just add the translational kinetic energy and the rotational kinetic energy, and then we're going to do as we usually do, where we have L equals, the Lagrangian equals T minus U, and we would have to do the Euler-Lagrange equations. But as you can see, the algebra is significantly more difficult than the previous problem, and in the previous problem it was tedious enough. So you can do this, but you would have to definitely use Mathematica, and even then it would be pretty tedious. But it's okay if we approximate ours using just the ideal point mass sort of case. So any questions about the double pendulum? So the double pendulum is actually quite difficult to study analytically because the equations are so complicated. I mean, physically, mechanically, it's very simple, but equation-wise, it does get complicated. So we won't study this analytically, but we can do some numerics on it. So that's basically what we're going to do. So if there are no questions, we could do some experiments then. So next week, Professor Blackmore will actually give you guys a lecture on